Hi, my name is Ari Benjamin, and today I'm going to explain to you how gradient descent can explain human-like psychophysical phenomena. Human perception is not perfect. We can detect certain types of changes better than others. For example, if you look at how well we can detect changes in orientation, you'll find that we're better at detecting changes near vertical and horizontal than the diagonals. This is a classic feature of psychophysics known as the oblique effect. And being a pattern, it must reflect something about the way we see the world. One clue is that this pattern of sensitivity or detection thresholds is similar to the frequency of things in natural images. With certain orientations, the vertical and horizontals, are more common than others in natural scenes, and we are better at detecting those more common orientations. Now, detecting more common things is a good strategy, or detecting more common things with greater fidelity than others is a good strategy for perceptual sensitivity when your goal is to encode the world, but you can't do it perfectly. For example, there could be unavoidable noise in the nervous system or an architectural bottleneck that limits coding ability. Now, despite this constraint, you could minimize your average error by allocating resources to encode those more common things with greater fidelity than others. Now, today I want to present an alternative explanation to this classical framework. Instead of being limited by some explicit constraint like noise and coding optimally despite that, I want to convince you that otherwise unconstrained encodings with no noise or a bottleneck, for example, are implicitly limited by having learned with gradient descent. Now, the first line of evidence comes from artificial neural networks trained on natural images. We can measure the sensitivity of networks like this by presenting oriented stimuli and observing how the activations in various layers change when you change the orientation. Doing this on a couple architectures, we find that indeed the sensitivity as a function of orientation is higher at the cardinals than the diagonals, and that this pattern matches that of humans. This is notable because these networks are noiseless in their processing and are large enough to represent images perfectly, at least in principle. So what this means is that we can't explain this effect with a framework of optimal coding despite noise. To see if gradient descent alone could explain this sort of phenomena, we constructed a toy example. Specifically, we took some input data, X. Here are some image patches from natural images. And we trained a matrix W to essentially do nothing, to pass those X through and yield something as close as possible to the original X. So the solution is for W to be the identity matrix. This is an unconstrained problem. It's totally learnable and should have equal sensitivity across all things, at least in the final solution. But at intermediate training times, something different happens. In natural images, the principal components these are, if you do a linear deconstruction of the natural image database, you can see various components that describe natural images, and these components vary in, for example, their spatial frequency, such that those components with very high variance or a large singular value have rather low spatial frequencies. Now, when you train to reconstruct images through this single matrix, there's some nice theory pioneered by Andrew Sachs and some others in the theory of deep learning that shows how the principal components in this reconstruction task are learned in order of their singular value, so in order of their variance. So earlier principal components are learned before others, and this is shown in the right plot, where blue or earlier principal components reach the fully learned thresholds here at 1, before even, say, the 50th principal components is even begun to be learned. We can schematize this process as being related to the sensitivity of the output, so x hat, as follows. if you have some feature like hue or here color, and it has some empirical frequency, the dynamics of gradient descent, both in this reconstruction test, but we can show that this is more general to reconstruction. And details would be in a preprint forthcoming. But for these features, what we find is that the more frequent things are going to be learned earlier than the later ones. At infinite times, everything will be learned, so the sensitivity will be uniform, but at intermediate times, like T1, T2, or T3, it will appear as if the sensitivity tracks the empirical frequency. We think this framework can explain the dynamics of perceptual development. So on the left, I've shown some data now over 4 decades old about spatial frequency, the minimum observable spatial frequency that's at a given contrast for humans as a function of their age. So spatial acuity. And this increases as a power law up to quite an old age, around 10 years old. And it's the locus of this is cortical. It's due to learning. Similar things are observed after, for example, congenital cataracts are removed during the critical period. There's an increase in spatial acuity. This can be reproduced even with this matrix learning model by looking at spatial frequency, sensitivity as a function of the epoch. So I'd like to leave with a parting question. I talked about 2 different frameworks to explain non-uniform profiles of sensitivity, and ask how they might explain an increasing acuity with age. In the top, the noise framework, you might imagine that noise decreases with age. So there's high noise at young age, but the whole time infants are decoding optimally. On the bottom, we simply note that when training with gradient descent and perhaps other learning rules, there is an increasing spatial acuity simply by virtue of having more experience. Okay, thank you. Goodbye.